the forces that we have, in effect, excluding the gravity, most of the forces that we encounter in our day-to-day life are, on the basic level, they are nothing but electromagnetic force. So theoretically, it would have been possible to start from the atomic picture and deduce everything regarding the friction force as well, or for that matter, any other force except for the gravitation actually. So theoretically, it would have been possible to deduce all the things regarding friction. But the point is that there's simply too many particles involved actually. And therefore, quickly the problem becomes almost out of control. Yes, actually, Nilavrita is quite sweaty today, by the way. I've been sweating too much, doing some exercise a bit later earlier. And even now, the sweat is not. And the fan of this room is actually, the bearing has gone bad, so it just doesn't run. Okay. Yes, Nilavrita observed it quite correctly. But anyway, let us continue with the friction I was saying. So what I was saying is that yes, there are simply too many particles involved, and therefore the approach from the atomic point of view, though it is possible theoretically, however, it is going to be very complicated. And in any case, the assimilation of the entire result will be very, very difficult. So what has been done essentially is to come up with certain empirical set of laws. Okay, this always happens. It happens with the normal reaction as well, or it happens with thread tension as well. It has happened with the spring force over there. These forces, people have come up with empirical relations which has been obtained or which has been established by means of experimentation, basically. So we are going to do the same thing with the friction as well. In fact, we already talked about that. If we look at, for example, a heavy object, let's say a heavy box or heavy table, for example. In this case, if we try to move this block by applying a force on it, say we just pull it, with F is right now a force which can change over there. Now, what happens is if my force is too small or it's not very large actually, then it's a common observation that the block is not going to slide. It will simply stay there, which implies that my force must be opposed by some other force, and that is nothing but the force exerted from the ground, which is nothing but the friction itself. That's going to oppose my effort, and therefore the block does not move. Okay. If I gradually increase my force capital F that I'm applying, what will happen is up till some point it will simply not move, but starting at certain point it will start to move actually. And once starts to move, it is relatively easier to continue it pulling actually. The reason we have seen is basically because of those microscopic interlocking that take place. Effectively, if I just consider the surface of contact where both of them are touching each other, in that case, okay. If we just magnify this part over there, let's say we just magnify the contact. In that case, it seems that the surfaces are very irregular. They tend to possess dents and ridges over there. So in effect, the upper surface will be something like this, irregular and like a heartbeat effectively, while the lower surface also is having those irregularities, and these irregularities they tend to get locked at some places, not everywhere, but at least the locking is more prominent because this irregular nature. This is again a view which is a kind of model for us, model for the friction. It works quite nicely. In this case, if we want to move, yeah, definitely. What's the trouble, by the way? This view is quite fine. Whether new or old doesn't make much difference. Yes, Arkodev, Newton's law itself is 300 years old, by the way, but still works, isn't it? It is enough for us. I mean, if it is working, what is the point of discontinuing that, by the way? It just works quite well, so we just continue that same model. I said already that these irregularities are in fact, the the surfaces are not exactly very smooth, isn't it? So what happens is these irregularities depict at the almost at the molecular level the arrangement of atoms over there. Not exactly molecular, we can't go down to that much because that particular level will be very fuzzy actually. So it is more like still a macroscopic view, but say roughly 1,000 or 10,000 times magnified. You can just think of that one. In any case, the model works quite nicely. The fact is that if I want to start the block moving, in that case, we'll have to break these interlockings actually. So what happens is that takes some effort. Before that, when I was applying my force, the body was not moving, as a result of which the friction force, which is the only backward force acting in this case, will be exactly equal to the applied force F. However, and that will continue to be so, by the way, unless until the motion starts. That happens after some time. So till that moment, we have the variation between small f, capital F. As my force increases, yes, Ankit, I'm starting with friction today. Without friction, things are obviously not very exciting over there. So introduce the friction as well. So in this case, blue mark line, this one, Nilabrata, that is, I've drawn the axis, horizontal axis. Oh, that is the lower surface actually. This irregularity is the lower surface over here, and the black one is the upper surface. I'm just representing them by such irregular surface over there. I mean, that's the kind of model that we are working with, where in effect looking at this magnified picture of the surface itself, and that seems to be that way. Lower one is the blue one, blue diagram, blue line represents the lower surface, and the black one represents the upper surface. Okay. Fine. So what I was saying is that as long as our force does not exceed a certain value, then the friction force exactly equals capital F because it is not allowing the block to move. And that implies that small f is equal to capital F till that point, which is simply a linear equation. So the graph is effectively straight and 45 degrees. The friction is exactly equal to capital F. But this happens only till a certain value. As I said already, at the one point, these interlockings they simply give way. So they break effectively. Starting from that moment, the body starts to move. So till that particular point, the graph will increase, and at one point abruptly starts to move. So the graph, what happens is this lower surface will contact. Oh, well, actually, what do you meaning by that? If the upper body is placed on the lower surface, it will come in contact, isn't it? Contact in this case obviously is I would say a concept which is a very macroscopic in nature. Actually, I would say when I am touching, my hand seems to be in contact, but strictly speaking, they're never touching, by the way, isn't it? Because of the fact that if we just magnify them quite by very large amount, then there is simply no surface that we have over there. If it is very fuzzy, like almost like a fog or cloud, effectively, at that particular level, we shall not find any two surface. We just find two uh, different density regions actually, where density varies almost in exponential manner. Okay. Anyway, in this case, the idea will be to. This is just a model diagram. Say the upper block, the blocks at the black body, the black line represents the surface of the object, while the blue line represents the surface of the ground. Okay. So I'm just showing them that this irregularity is a kind of interlocking. Obviously, this interlocking can be reduced if I spray some powder, for example, a powder of very fine dust, whose molecules, whose particles, they can fill in the gaps of the blue surface. In that case, those interlockings will be definitely reduced, and therefore the surface become more smooth as well, isn't it? That is why, for example, on a carom board, we just sprinkle the powder over there. The powder is quite fine so that it can fill the gaps, fill the irregularities over there. And then the, what do you say, that carom coin, they can just slide on that with very less friction actually. Obviously, if you want to further reduce the friction, the best strategy will be to not allow them to just come closer, isn't it? So what can be done, for example, is we can just blow a layer of air in between them. There's something called an air table actually, or maybe you have seen them in game parlors. When you just go to game parlors, there is one game where we have a big table. There's a football kind of thing where there's a disc, and we just hit it with the say something which I'm holding, and then the other person in the other side has to stop that from getting inside the goal, isn't it? That's almost like a hand football basically. Well, bullet train also works almost similarly, but we are just considering, yeah, that can be said by the way, because it's effectively doesn't touch the track, so yes, it's actually floating a bit above. So that is the idea. Say if you want to further reduce the friction, the best strategy will be obviously to not allow them to come in contact at all. So that can be done by means of an air trap or air table. Normally, that air table contains a lot of holes through which compressed gas is pushed through them. So that basically the air table behaves almost like a fountain with a lot of air gap is there. So the air comes out of these little holes, and when the block is kept on it, it's basically floating on a layer of air actually. So in that case, the friction becomes very small. Fine, that can be done. Or maybe we can just keep a block of solid ice over there, so that will automatically say evaporate some of it, and then we shall get a cushion of air below it, in which case the body can slide without much friction, in fact, isn't it? Anyway, those are the methods that can be reduced. Obviously, it's not a very practical situation to take up solid ice, say dry ice, for example, the solid carbon dioxide, or for example, such an air track. It will not be feasible in most cases. So usually, greasing is the usual way that we use for machines. Actually, in case of machines, for example, grease is being used, which effectively kind of fill those gaps over there, and it is creating almost the same situation. Okay. Anyway, if I consider the force at which the body or the interlocking does just give way over there, that is the maximum friction which the surface can offer. At that point of time, the interlockings break, and subsequently this heavy block starts moving much easier actually. So this particular point is, yes.
So, what can we say about the friction between the water molecule and a pan means which is very very hot means I want to say about the Leidenfrost effect means
Yes, yes.
during that time a
Yes,
layer
sir.
of
That's
water
right.
develops between the two surfaces in contact. So therefore, the friction can be reduced to zero in that case.
Not zero. Air also exerts some friction by the way. It's very small comparatively. Yeah, Leidenfrost
Okay.
effect is something like, you see, possibly you must have seen this if your mom or anybody is preparing some chapatis, rotis, the pan is too hot. In that case, if you sprinkle a couple of drops of water, those drops can stay there for a long, long time actually. They almost behave like pearls, little pearls, which just float on the pan over there. Okay, have you ever seen this kind of effect? Sprinkle
Yes,
some water on a very hot pan. That is known as a Leidenfrost effect. Yeah, it's called a Leidenfrost effect. Okay, that Leidenfrost effect is effectively why it happens basically because yes, they just move. It happens. It will not happen with a pan which is say hot but not very hot. In that case, what will happen if you just sprinkle the water? It will evaporate quickly, almost entirely. But if the pan is too hot, actually, then the moment the water drop strikes it, a layer of water, or at least a part of water, quickly evaporates. And when it evaporates, basically the rest of the water is floating on a layer of water vapor, actually, because the lowermost surface, which was of water, which was coming in contact with the pan, it evaporates abruptly, very fast, and therefore creates a cushion of water vapor mostly on which this remaining water is floating actually. Fine. Yeah, and normally air, or for that matter, water vapor as well, is a very bad conductor of heat, in fact. So what happens is it serves two purposes. First of all, it reduces the friction to negligible value. The second thing is that it also doesn't allow heat to transfer at a faster rate between the pan and the drop. So drop lifetime becomes quite large. In fact, some of the drops can be sustained. They can remain over there for more than 1 minute. Actually, it becomes so much. The name is called Leiden-Frost effect. Leiden-Frost. It's Leiden, L-I-E or L-E-I. I've just forgotten by the way. I possibly
Sir,
what?
sir, LEI.
Okay, L-E-I-S. Leiden-Frost. That is a name. Leiden-Frost effect is what we have. Yes, Ananya, what I was saying is, in this case, when the pan is too hot, actually, it's very hot. It will not happen with pan which is hot but not too hot. Actually, when exactly what is the meaning of no total water will be vaporized, but it will be gradually. Actually, if the pan is not so hot, the pan this water drop will just spread on it, and the entire layer will evaporate. Okay, but if it is very hot, actually, what happens the moment that particular droplet touches the surface, the lower layer of water, which is coming in contact with the pan, it evaporates quickly. Fine, it absorbs the heat and it evaporates quickly, very fast actually. And when that evaporates such fast, it is not able to escape. It is basically because above there's some water, so it's not able to evaporate, not able to escape actually. So what happens? It just forms a cushion of water vapor just between the droplet and the pan, and on that cushion of water vapor, this droplet over there that floats. It serves two purposes. What I was saying. First of all, is that this will obviously reduce the friction to a very small value, which is for our purpose interest over there. The other effect will be that this water vapor or air in general is not a very good conductor of heat. So now the rate of heat transfer between the two is reduced to very small value, and therefore this will evaporate at a very slow rate. In fact, it can just remain there for a long time. By the long time, by roughly a minute, it can just stay there for more than 1 minute. In fact, okay, that is what we have. If the pan is not so hot, it will be quickly evaporated. But for very hot pan, this is what going to happen actually. Okay, this is the Leiden-Frost effect. So yes, who asked this question by the way, Orkodev or Riktam? I think
Sir, Obrodi.
Abradeep. Okay, fine. I was not looking at the list actually. Fine, good question. Anyway, if we come back over here, just looking at the mechanical effects first of all. In this case, I was saying that once the water temperature of the pan, well, I think it will be roughly around 400 degrees Celsius. I think so. It will definitely not work with 200 degrees Celsius or something. It should be hotter than that, roughly around 400 degrees Celsius. It will be interesting experiment to record the temperature and see. No, it's not red hot by the way. I don't think it's red hot. Red hot is not. Have you ever seen a pan which is kept on the stove red hot over there? I have never seen such thing to happen.
So any pan doing chapati will do.
Yeah,
Like that.
any pan on which chapatis are made can be. It will not even. You can just put a plate on the stove as well. It will also work. Okay. It has to be very hot. However, the exact temperature I do not remember. Maybe we can just figure out later on over there. It should not be red hot by the way. Any utensil work actually. Obviously, it should be made of metal. Plastic won't work. Ceramic will not work. I believe so. Metals are going to be there. Okay, just wait. Let me just try to see if we can find it out. Leiden-Frost effect, temperature.
So it's saying 193 degrees Celsius.
Only. Oh yes, approximately 190. So say I'm wrong by the way in that case. It's actually around 400 Fahrenheit. In fact, it was not for degrees Celsius. I remember that number. It was 400 Fahrenheit roughly, 379 rather. So it's roughly 200 degrees Celsius will work actually. At 193 effect will happen. Yes, Tiasa, regarding the friction, yeah, it implies what this part. Oh, how it becomes zero? Where? In which case it becomes zero? I'm talking about this situation. Okay, in this case, the friction is negligibly small because in effect the droplet is floating on a layer of water vapor, isn't it? The friction supplied by the gases is very small. Gas exert very small friction at nominal speeds over there. Normally, small speeds they offer very small friction. That's what happens in this case. In this case, it's just floating above a layer of air, to be more precise. That is why it is feeling no friction over there. Fine. First of all, okay, Ananya, the impurities this should affect the entire thing quite obviously, because if there are heavy things which are dissolved, in that case they will not easily evaporate, so it will say affect it definitely. But exact way again we have to just experiment. Haven't just seen what happens with salt water or sugar water or sand water, for example. Why very hot temperature will lead to this? Not a bit. Actually, when the temperature is not so high, it does not evaporate abruptly. Say in this case, what happens is the lower layer must evaporate quickly. Okay, otherwise this effect will not be. Otherwise, this layer of air will not be formed actually. If the temperature is not so high, say 110 degrees Celsius, if you just do that, in that case, the heat transmission is almost uniform through the entire droplet because the lowermost part is not abruptly gone. So in that case, it is very, slow process, and so it takes, or the heat gets time to spread through the entire drop, and that is why it is not going to be seen. In fact, okay. Talk about that later on in case of thermodynamics, I believe. But the main ideas should be clear enough. Yeah, they will be differing in rates actually. And this must happen. What should happen is the heat absorbed by the lower layer should not get transmitted to the upper part. So lower part has to get the heat quite fast, and but the upper part they haven't got yet the chance to do that. Okay, if the temperature is small enough, for example, in that case the convection current which takes place within the droplet will spread the heat more or less throughout. Okay. Which should not happen. If that happens, in that case, this effect won't be visible actually. Okay. Anyway, so if I just consider this one, will happen with solids that will undergo sublimation. Strictly speaking, yes, Atri, it should happen because again the same effect will be there. They will just form a layer of air or vapor below it, and then it can be seen actually. Yes, that should happen in fact. The easiest thing to see that effect in picture is to take up dry ice, which is solid carbon dioxide. That behaves exactly the same way. It will just evaporate, and so there will be a layer in between the ground or the surface and the block of solid ice, and this effect can be seen as well. Yeah. So in this case, what I was saying is, if I once this once this interlocking the break actually, subsequently the friction drops slightly by the way. So approximately after it becomes roughly a constant. That is how the behavior is. There's a kink which shows that the maximum friction which takes place, or the maximum friction offered by the surface, is slightly bigger than the kinetic one. This part represents the maximum friction or limiting friction that we have. The limiting friction is slightly more. I can write down F max. This is the maximum friction or the maximum value to which the friction will increase. Subsequently, it decreases slightly actually. Once the motion starts, once the body is sliding, it is relatively easier to maintain the motion because these interlockings are not able to form now actually. And that is why this value has gone down slightly over there. And subsequently, it is more or less going to be a constant. The kinetic friction does not change much. You can see the static friction, which is basically this portion over here, this part, that is a static portion, or the static friction part, that is a kinetic. The static, this is kinetic. The static friction is a variable force. It can just change depending on the external situations. The static friction is going to vary, but the kinetic friction is a constant. Okay, this is one thing that we observe. Second thing we notice is that the maximum friction is of all this situation, no matter what, whether kinetic or static, the maximum friction occurs at this particular point, which is the maximum force, and we shall see just now that the maximum force is actually proportional to the normal reaction. Yes, Satri, that is always correct. The static friction is not always. The maximum friction is always more actually. Static friction, you could see static friction in this case is this much as well, which is definitely less than the kinetic friction. So you cannot say the static friction is always more than kinetic one. That we can't say. But what can we say is that the limiting friction or the maximum friction, that is the one. Yeah, the limiting starting friction, this one, the limiting static friction, that is definitely more than the kinetic one. That can be said definitely. Yes.
Sir,
Yes.
so why the transition region between the static and the kinetic friction is
Yeah.
structured like that only? Means why
Because
it
ideally it should be just abrupt. Ideally, it's going to be just it increases and then suddenly it just goes down. Ideally, it should be like this for ideal objects. But in real life situation, that doesn't happen. It has to decrease gradually. Okay. Because at that time part bonding is going to be there. Part of these things will be there. So it gradually decreases.
okay,
Ideally,
sir.
however, this is what should have got, because it goes up and abruptly comes down. So that should happen ideal situation, but reality it will be slightly uniform. No particular pattern in there. I mean, this part over here, this part, no. Say it doesn't matter. It doesn't seem so. Reality, you can just make it smooth. Otherwise, it may be third of something like this, gradual, almost an exponential decay over there. So no, technically speaking, nobody has seen that pattern over there. It could be seen definitely, but I don't think that is. Well, it's always correct actually. The point is when we study about physics or any other things, whether we are actually talking about a certain model, we are not actually looking at the actual thing. We are always only studying about the model of it, because the actual thing to do will be very, very complicated. So just try to make up a model of it, a theory of it, and then study that. Okay. If it is able to explain most of the situations, then theory is quite successful. Otherwise, it is not. For example, we already know of Newton's laws. It's quite a successful theory, though we know it is not exactly correct. But anyway, that's fine. As long as it works, it is okay. Based on all this classical theory, all big structures have been made, bridges are known, skyscrapers have been made, say rockets have been made. They're all based on the same classical physics, and they still work, isn't it? We have to reconsider it later on actually. Once we are going to be doing in more detail or more precision, in that case, we'll have to reconsider that definitely. Okay. Anyway, this is what we have so far follows from observation. Yes.
So why the value of kinetic friction comes down from that of
This one.
limiting friction? Yes, sir.
It's slightly less because you might think this way that once the bodies are moving, these interlockings not able to form completely. So it will require relatively lesser effort to move them actually. Okay. But
Okay,
once
sir.
the moment they come to rest, in that case they'll again form quite strongly. But when when one body is moving above the other one, in that case the interlocking are not able to form completely. That is why the kinetic friction is slightly smaller. Fine.
Okay, sir.
Okay. Okay. Now the empirical rules that we have for the friction. The first thing is regarding the direction. What about the direction of friction, by the way? In which direction the friction is going to act? Anyone?
Opposite to the motion.
Opposite to the relative motion.
Yeah.
Yes, sir. Opposite to the yeah.
It should be actually friction is not opposite to the motion, but opposite to the relative motion. Friction always opposes relative motion. It may happen in certain situation that the force of friction is actually in the direction of motion of the body, but the important thing to notice is that it will try to oppose the relative motion. Okay, that is one thing that we have. The direction of friction always opposes the relative motion. But in bodies, the relative term is important. That's the first thing. So usually, like while walking, well, yes, definitely. If there was no friction, while we walk, for example, what we are doing is actually we are pushing the ground backwards. When some person is walking, let's say the skeleton, how does walking look like? Till there, we have the front leg, the leg it becomes smaller bit. It's almost like a weird way to walk actually, but nevertheless. Say for example, this skeleton of the person, yeah. After motion between the bodies. As we have in this case, the idea will be to just with the rear leg going to push the ground. As we are pushing the ground is going to push us forward, and that is how we move effectively. So if there was no friction, we won't push the ground, and the ground won't push us, and so we can't move effectively. But anyway, the point is not what I was not specifying on this point, by the way, but the point is the usual way that you can obtain the direction of friction is to think what might happen if the friction was not there. For example, suppose I consider a block over here on top of which another block is placed above it. This one, this is 2. Or maybe say, for example, something like this we have. Okay, so we tilted, but let us see. Just straight. That's it. The difference of perspective, there is a trouble. More or less straight over there. So in this case, we have one block placed on top of the other one. And say, for example, I just pull on the lower block. The lower block is pulled towards the right. So what will be the direction of friction on the upper block, by the way? As long as, I mean, whatever.
So in the direction of the block.
So the force of friction will be along the direction of motion of block 2.
That is towards the right, isn't it?
Yes, sir, towards the right.
The usual idea how we determine the direction in this case is to first of all assume what might happen if there was no friction between the two surfaces. If there was no friction between them, for example, this block 1 will just stay over there. It will not go anywhere, but the 2 will just go below towards right. If there was no friction between these two blocks, imagine for the moment there is no friction. In that case, this can't go anywhere, basically because there is no force acting on it. We are pulling on this one. We are not pulling on directly. On one, therefore, the only force acting is vertical. It is therefore not experiencing any horizontal force. So if there was no friction between them, what will happen is this will just simply stay over there. And this will just go towards the right. So as seen by, for example, this 2. With respect to 2, we find that 1 is going backwards. Not from the earth. With respect to the earth, this one remains there. 2 goes towards the right. But with respect to 2, 1 goes towards the left. And therefore, 2 will basically, that is a situation as seen from 2. So with respect to 2, 1 has a tendency to go towards the left, or it is moving towards the left, has there been no friction. So once I switch on the friction cannot reverse the motion. Friction cannot reverse the motion, but it can only retard it. So once I switch on the friction, the tendency of 1 will still be to move towards the left with respect to 2. So 2 will exert a force on 1 towards the right. Okay. That's the idea that we can apply in most cases. I mean, most of the time it's going to be quite simple, but in some cases, you'll have to think about exactly which direction the friction might be. So in this case, for example, the usual idea will be to think what will happen if there was no friction. Once the motion is going to take place with no friction, the direction are known of the motion, and once the friction is switched on, the direction cannot be reversed. So we can just figure out which direction the friction will act actually. Okay. So at least in this case, we can see that the friction act on 1 towards the right, and that is the direction of off motion actually. So in this case, friction is not opposing the motion, but the relative motion actually. Fine, that is what we have. The second thing that we should keep in mind is the relationship between the friction and the normal reaction between the contact. If we talk about a body which is in contact at this point. So the friction at any given contact is going to be proportional to the normal reaction at that very contact actually. So the first thing is that the maximum friction, limiting friction. The max friction is equal to mu s into n. Mu s is known as the coefficient of static friction. This is max as a coefficient of static friction. This is a number which has to be experimentally determined. Last 2 minutes I was just talking about the law actually. I just said in last 2 minutes that if we want to find the direction of the friction, we can start by assuming what will happen if there was no friction. So if there is no friction, we can figure out the direction of movements or the motion of the bodies, and then in accordance, accordingly, if we switch on the friction cannot reverse the direction of motion, but it can just retard it. So the tendency of the bodies will be to still move in the same original direction that we earlier figured out, and accordingly we can find out the direction of the friction uh, uh, between the bodies actually. Okay. The second thing that I was saying is that F max is nothing but mu s, and that is equal to the coefficient of static friction. I was saying that this mu s, this coefficient of static friction, has to be determined experimentally between various pair of bodies, and mostly it will be available in some handbooks over there. As far as we are concerned, the data will be given actually. Okay. The third point that we have to keep in mind is that the kinetic friction, or rather, I can just say once again for static, say as long as the body is not moving, or in case of no slipping, implies when there is no relative motion between the bodies. As long as there is no relative motion between the bodies, the friction force between them will be either less than or equal to the maximum friction. So we could write on this. F max is the maximum friction, which is a static one, which happens when the body is just on the verge of breaking the, motion over there. But otherwise, as long as there is no slipping, we can say that F is less than or equal to mu s into n. It may be equal to mu s into n, but it may not be. It can be less than that as well. So we cannot be very sure unless and until we know that there is slipping actually. If there is no slipping, then we cannot say always that F is equal to mu into n. That would be wrong actually. Fine. So keep that in mind. And the final thing is that the kinetic friction is again equal to mu k into n. So once the body or once the slipping starts, once there is relative motion between the bodies, now F becomes equal to mu k into n. But before that, as long as there was no motion between them, then F may be equal or less than mu s into n. But once the motion starts between them, there is nothing but the kinetic friction, which is nothing but mu k. Slipping is implying there's a relative motion between them. Slipping implies relative motion between them. Between the bodies, basically. So, if there is no relative motion between the bodies, then we say that they are not slipping. If there is relative motion between the two bodies, in that case, they do slip. So when there is relative motion, the acceleration will be different in general of the object and with which it is in contact. Okay. These are laws that we shall utilize while applying the idea of friction. Actually, friction becomes, or it complicates matters basically because we do not know whether it's going to be maximum or no. Asha, there's one more thing, but if nothing is specified about mu s and mu k, then you can take them both to be same thing actually. Point 4, I've written down Fk is the kinetic friction. Fk is the kinetic friction that is equal to mu k into n, where mu k is the coefficient of kinetic friction. Okay, mu k is called the coefficient of kinetic friction actually.
Sir, can you give an example where the objects are not slipping?
Yes, I can definitely give an example. Uh, we just take this one itself. When this body, for example, I just drew, we had one block over there, and above it is another block, and I'm exerting a force on this. It might happen the force is not too large. In that case, these two will just move together. It might happen, isn't it? That is you can always see it by doing experiment. For example, take one book and above it put some other block or another book. In which case we can have this. For example, there's a block like this. This is a block kind of thing, and we just place it on a board like this. And in this case, if it is, you see that if I am pulling it, just moving this way, not slipping. But obviously, if I pull it suddenly, then there's motion actually. Or we just put with large force, there's an acceleration which is too large, too much. You see, friction can only grow to a certain value. In this case, for example, what's happening is the acceleration to this block is being provided by this force as well as friction over here and over here. But if I consider the acceleration of this block, it is only provided by the friction at this contact, and that can have only a certain maximum value. So if the acceleration is too much, for example, in that case, the friction will not be enough to provide that acceleration, and therefore they will be slipping in between them. But if the acceleration is not too large, in that case, friction is enough to provide the required acceleration, then it will be able to do that. Okay. Yes, if there's only mu given in questions, we just take them to be the same. If it is given only one single mu in the question, single coefficient of friction, then we just work with that one, assuming this to be both kinetic as well as static. Okay. And this is usually the situation. In most cases, we shall be given only one coefficient actually. In that case, we just take them to be meaning both kinetic as well as static. Okay. You see, if we know that the body do slip actually, in that case, there's no problem at all. In that case, for example, if I consider an inclined surface on which a block is placed and it is sliding down. Let's say if you consider an inclined surface like this, say that we have a wooden board which I have hinged about this point and I can place at different angles. There's a wooden board and it has been hinged, for example, like a door. At this point, this line over there, and can just rotate about this one over here. So in that case, for example, if I just keep a block over here and try to see what happens, if the angle is too small, if this angle is too small over there, theta, if the angle is too small, then quite obviously the block will not slide actually, isn't it? If the angle is too small, in that case, the body will not slip. As I gradually increase the angle, at some point the slipping starts. Fine. If I gradually increase the angle, at some point the slipping starts. That particular angle is known as the angle of repose actually. The angle at which the slipping starts is known as the angle of repose. Okay. I hope you know this angle of repose. It is specifically linked to such a situation. The angle of repose is basically the angle of the incline at which the slipping starts. Slipping starts, right? We can show in this case that the angle of repose, if we know this angle, the coefficient of friction can be figured out actually. You notice in this case that as long as the block is not moving, or just when the verge of slipping, at the very moment, if I take this angle to be the angle of repose over there, if theta be the angle of repose, at this moment we can draw the FBD of the block, the free body diagram. At this instant, when this is on the verge of slipping actually, in that case, if you look at the forces, mg pulls it down, the gravity, there's normal reaction from the surface, and there's a friction. These are the only forces that we have. If you look at the FBD of this block, in this case, we have one force, mg, pulling it vertically downwards. We have a normal reaction pushing it away from the surface, and we have the force of friction, which is pulling it up the incline actually. Now, because in this case, I said because the body is just on the verge of slipping. So at this instant, it should happen that F and mg component down the incline are exactly balanced. This is in fact the maximum angle for which they are going to be balanced. In fact, if I consider this angle with theta as well, the component of mg will be two. One is going to be this way, which will mg sine theta. The other component will be that way, which will be mg cos theta. So in this case, if I look at the components, this becomes mg into cos theta, this word component, and this becomes mg sine theta. Obviously, once I resolve them into components, I cannot take mg again. So mg, you can just forget about mg now. We just written down them in two components, one down the incline, the other one perpendicular. So yeah, in this case, at this particular point, because on the verge of slipping, that implies that F is nothing but mg sine theta. Then N is going to be mg cos theta. And because it is just on the verge of slipping, therefore F must be mu into N, or rather it should be mu S into N actually. Just at this moment, because of the verge of slipping over there. So from these three equations, I can just divide these two to get F by, from these two equations, I end up getting F by N equal to tan theta. But then F by N is also mu S. So we end up getting mu S equal to tan theta, which implies that we can actually obtain the coefficient of friction by finding the angle of repose. So one of the practical methods which can give us the coefficient of static friction between the object and the body actually, the inclined surface. By the way, once the body starts to slip, what happens? If the angle is angle of repose itself, what will be the motion of the body block in this case, by the way? If we assume that the angle of repose is right now the angle, will the block move in this case?
No, sir. It will be in the verge of motion. Means it will be in the state of impending motion.
But it won't move.
It won't
It will
move.
have
No,
a
sir.
tendency to slip, but it will not just slip then.
Okay, fine. So if we just gradually increase theta, then slightly,
So then it will start moving.
and
So
then
then
Yes,
it
sir.
will start moving.
and then it'll accelerate down as well, because once starts to move, it won't be constant velocity actually, Rahul, because the moment it starts to move, the kinetic friction will act, which is slightly less than the static one, and so it'll actually accelerate, right? Because then friction becomes a bit less, while mg sin theta remain the same value, but this has become a bit smaller, and therefore it'll actually going to accelerate, not move with a uniform speed. Okay, but yeah, if we just do not consider that, then it's going to be just a uniform speed over there. Okay, fine. So if I assume for the moment, let's say for example that the angle is slightly more than the angle of repose, what would be the acceleration then down incline? If we assume that the angle is more than the angle of repose, what we have written last, this one is mu s equal to tan theta actually. Mu s equal to tan theta. But theta is the angle of repose actually. So by knowing the angle of repose, we can actually find out the coefficient of static friction actually. So that is one possible way to do that. The experiment will be relatively easy to perform actually. Okay. I said it will not be exactly moving with a constant speed because the fact that the kinetic friction is slightly lesser than the static one. So the moment the body starts to move, the friction will now become a bit smaller. And so this will be the same value, but this F has become a slightly smaller value. And so what will happen now is the body is going to actually accelerate down. So it will gradually increase in speed over there. Okay. It will not move with a constant speed actually. However, if I neglect that fact and just know, okay, that mu is same value, then it's going to definitely move down to constant speed actually. Okay, fine. So if we consider that the angle is more than the angle of repose, what will then be the acceleration? Say that the coefficient of friction is just mu, no mu s or mu k, or let's say mu k is known over there, because once the motion starts, mu k is the one which is more important. To say that we know the coefficient of kinetic friction, between the object and the surface, and it is known that the angle theta is more than the repose angle actually. So then what will be the acceleration of the block in this case, down the incline? What will be the acceleration?
So theta
Yes.
minus mu cos theta.
What?
So it's
G.
into sin theta minus cos theta.
Okay, fine. There's G into sine theta minus mu cos theta, isn't it? Yeah, that's fine enough.
Yes.
Because in this case, the friction will be nothing but mu times n, and n is going to be, if there is slipping, motion between them. Let's say, for example, this theta is no longer the repose angle, something more. In that case, we can have down the incline, we get mg sine theta minus the friction force, and that is equal to mass into the acceleration down the incline for this object. At the same time, perpendicular to that, there is no motion because the object is not jumping, so n must be mg cos theta. And finally, we have the equation because slipping is going to take place, therefore f must be mu into n, where I'm assuming mu is nothing but mu k actually, okay? So we can just put it back in this, this becomes mu into mg cos theta. We put it back in this equation, and so we end up getting the acceleration over here as g into sine theta minus mu into cos theta. So we have the acceleration. Okay, fine. And what will be the acceleration if I throw the block down from the incline, from the lowermost point? If I project the block upwards, so for example, same situation, but this time the block has been projected up with certain speed. In this case, I just projected it upwards over there. In this case, what will be the acceleration of the block? If I do the same situation, but instead of slipping down, the block has been projected from the below or lowermost point. So in this situation, what will be the acceleration of the block?
mu cos theta.
What?
G into sin theta plus mu cos
G
theta.
sin theta plus mu cos theta.
Okay, fine.
So it should be plus G sin theta
Yeah.
plus mu cos theta.
Okay, that's fine. That's fine. Only plus. Okay, fine. It's okay. Three, the last two steps. Last two steps, first of all, this one is fine. Three, this one is okay. So this time I have considered the motion perpendicular incline. This direction, there is no motion actually. In the direction normal to the inclined surface, there is no acceleration. So m into a must be 0. And that is why net force in that direction must be 0. So I have got n equal to mg cos theta down over there. And finally use the fact that because the body is slipping, so f must be mu times n, which makes it mu into mg cos theta. This one comes from the fact because there is no acceleration in this direction. And this equation comes from the fact that the friction is slipping and the bodies are slipping. So the friction is nothing but mu into n. Well, mu is the kinetic coefficient of friction actually. Okay. And once I've got that, I just put this f over here and divide by the mass to get the required acceleration. Okay.
Sir,
Yes.
so in the second question, sir, it should be retardation.
Well, acceleration doesn't mean that it is not a retardation. It is just happening that the acceleration is g into sine theta plus mu cos theta down the incline. That's what we have.
Yes, sir. Yes.
The retardation is simply the acceleration which is slowing down the object, isn't it?
Yes, meaning velocity and acceleration are in opposite direction.
Exactly. That's the retardation. And so in this case, the acceleration of the block will be simply, everything will remain the same except for the fact that friction will switch direction because now the motion is upwards. Then the friction will be acting down the incline actually. This will also act down the incline. Friction also acts. In fact, the ability have changed slightly by the way. Now the friction acts this way. That is the direction of friction as well in this situation. Everything else remains the same. The acceleration direction is also switched. Yeah, I mean the acceleration is still downwards by the way. Though the motion is upward, but the acceleration is still down. This is still a direction for the acceleration because that is the direction in which the net force is acting in fact. Okay. So in this case, the only thing changing is basically this minus becomes plus because the two forces in this case are acting in the same direction. This will become a plus over there actually. In this case, we shall get a plus sign over here. And these two together must be having an acceleration. But remember this A is still down the incline, okay? A is still down the incline, A is not up the incline, A is down the incline. Everything else remains the same actually. So this becomes plus over there as well. Fine. Okay. So in effect, while dealing with the force of whenever the friction is present, the only thing that we have to just take care or we have to just keep in mind is whether or not there is slipping taking place or not. If there is slipping taking place, then it becomes very easy. Then it is simply you just put F equal to mu into N. But if there is no slipping, then you have a problem by that. Then you have to just determine whether the tendency is to slip or there is simply no tendency to slip. Then we have a bit of problem actually. Let us see some examples. This is for the downward. I hope it can be done by the way. I think everyone has done it. Why A downwards? Why A3? Because the net force is down inclined. You see both the forces are acting downwards. And Newton's second law is what? F net equal to mass into acceleration. Isn't it? A3. The Newton's second law says that net force acting on a body is nothing but mass into the acceleration of the object. The acceleration and F must be the same direction because mass is a scalar quantity. Nilabrata, what did I say? I just said that there we're going to just do some examples. I hope that this has been done by everyone actually. So what will become difficult? Yeah, what I was saying is that the questions involving frictions are going to be difficult if we are not knowing to begin with, or basically because we do not know to begin with whether or not there are going to be some relative motion actually. If I know for sure that the bodies are slipping on each other, in that case it becomes rather simple. But if you do not know, then you have a problem with that. Okay. We shall see exactly how to approach that particular situation by the way. Normally when you deal with friction, second situation, block is moving up. Oh, well, the block was projected upward by the way. It was projected up the incline. We're just throwing it up the incline stuff. We're throwing it this way. Okay. It is being thrown upwards. And in this case, the velocity is this way. But the net force will be down the incline. As you could see, both the forces, mg sine theta and the friction, they're both acting down the incline. So accordingly, the acceleration must be downward as well. A3, is it fine? The direction of the acceleration determined by the external forces. Okay. In this case, that is why I have taken it downwards. Or you could have assumed it to be upwards, but then it will turn out to be negative. However, with friction, that is not usually a good idea to do that actually. Because if I assume an upward acceleration, then actually friction, well, in this case, moving the velocity. The body is moving up. Okay, Atri, what do you think? If I throw something up, in which direction the acceleration is there? Say body is projected upwards. So in which direction there is an acceleration of the body? What do you think? Down. Why? Why it is down? Yeah, the same thing over here. It is down because the only force acting on the body is mg. And that is actually downwards, isn't it? The only force acting on the body when it throws something up, I'm neglecting the air resistance, is the force of gravity. So gravity pulls it down. And therefore, if I divide by m, we get g downwards. Same situation. In this case, when I throw something up over there, up the incline, the component of gravity is acting downwards. And the friction is also acting downwards. So where's the acceleration going to point? It must be down because all the forces are down the incline. Isn't it? Because all the forces are down the incline. That is why, in this case, the acceleration must point downwards. You remember that in kinematics, we talk about the velocity and then the acceleration, but there was no need to proceed any further. We didn't define like what is the rate of change of acceleration. By the way, we didn't give some any special name because it's not required. Because the acceleration is the one which is related to the net forces actually. So there's no point of going ahead. A variable acceleration is what we have simply. If A also depends on time, then simply a variable acceleration. Nevertheless, we say F just relates the acceleration with the say forces. So that is enough to consider till the acceleration only. Okay, so the acceleration is determined by the external forces, that we must keep in mind. In this case, because all the forces are pointing down the incline, so the acceleration must be down incline as well. Okay. This is a vector equation. Keep this in mind. This is a vector equation actually. That is why we should. Force and the acceleration must point in the same direction because m is a scalar actually. Right. Okay. Let's see. Refill the pencils. Say we have a situation like this, where this inclined surface, a fixed inclined surface, on which we have placed a block of mass 8 kg. This inclined is fixed; it cannot move over there. The thread is massless. This thread passes over this frictionless and massless pulley. This particular pulley is frictionless and massless. Over there. Fine. And this thread goes on to is tied to another block, which is suspended. This mass is 5 kg, let us say. This is a 5 kg block suspended like this. Okay. So, and there's a friction as well in between the two surfaces. There is some friction. The friction coefficient is only one of them is given 0.01, for example. It's too small. Let's say 0. Just a moment. We have to, okay, fine, let's take some specific value by the way. We just consider in this case mu to be 0.01. Quite smooth, almost smooth over there. 0.01. Okay, that's the coefficient of friction. We shall see what happens. And subsequently, so once this system is released at rest, we release the system at rest. We'd like in this case to obtain the acceleration of the system. Once released at rest, determine the acceleration of two blocks. The friction is acting at this point over here. Once released at rest, determine the acceleration of the bodies. That is a question we deal with. First of all, I would like you to draw the FBD for, yeah, this wedge is fixed. That is a fixed wedge actually, that's not moving.
Sir, so
Ah.
what will it take is equal to 10 or 9.8?
G.
Yes, sir.
Take it 10 for a moment. 10 meters per second square. Five point 7.715. Let us see. Well, the answer I have to figure out, by the way. Nishant, just let me find out. Hold a moment.
So is it 3.2?
Wait, let me see. Just a moment. Since the friction is too less, right, in this case. Well, if you take G as 10 meter per second square, then it is turning out to be approximately 1 meter per second square, actually. Yeah, it's actually 1 meter per second square what we have. Not 0.9, it's more like 1.0 something, in fact. More like 1 meter per second square is what I'm getting. 3.2, no, 19.28. Yes, 1.03 meter per second square. Okay. 0.7. No. I am getting to be no, it's 1.0 something. If you take G as 10 meter per second square. Yes. Atul, 0.715, it is not, okay. Okay, just wait, hold a moment, hold on. I mean, how can you get so many answers, by the way? Either of how many got 0.7? 0.7, I don't think anybody has got, by the way. I mean, voting won't work in any case, by the way, isn't it? Okay, first of all, in this case, which direction the object is going to move by? Sir? Can you tell me that? In which direction there is motion? Whether it's going to go down or up? What do you think? Going to go down. Well, that is fine. In that case, we've got the required result. It will be down. 5 kg is going to go down. Okay. Let's see. You see that
So many are getting 0.7 of like that.
doesn't matter on it, even if many are getting. It won't work out to be that way. Even if
So
many.
once it happened,
What?
yes, sir, once it happened in a tuition, two voted for me and one boy voted for a thing, and another 5 voted for a thing, but we two won.
Is it this is a parliament or what? Voting won't work over here. Either you get a correct answer or applying the laws. Democracy is fine, but the physical system doesn't follow your democracy.
Sir, so the teacher also has the democracy to cut marks in that case.
Yes, I mean, say if all of us decided, okay, no, sun doesn't rise in the east, it does in the west, will it work? If everyone does so, in that will work because I'll just simply rename the direction from east to west over there. But otherwise, if 100 people say that sun rises in the west, doesn't matter that it does. Anyway, let us see. The first thing is to notice that this is actually going to slide down. That happens, okay, if I just want to figure out why it happens so, then okay, that is more or less correct. At least academics does require a bit of dictatorship, otherwise people will simply not study. The block will still get confused. Yeah, that's fine. It may get confused, but I don't think the block is going to get confused. It will just simply slide in whatever it's trying to do that by, with whatever acceleration it has to do. Anyway, the first thing I need to in this case see is what will happen if there is no friction, for example. If there is no friction, then things becomes rather simple because we already seen that this is simply like an adverb machine. This will be actually accelerating downwards or upwards depending on how much is 8 into sine 30 degree. In this case, 8 sine 30 degree is just 4 kg, which is less than this 5 kg. And that is why this is going to go this way. So that much at least is known that when there is no friction, this system will actually accelerate this way. This will go down, this will go up. So when I switch on the friction, I can't reverse the motion. What can happen at a max is it will just simply not move. That is worst possible scenario. But in this case, it does move. And because if I assume that it is not moving at all, then the friction would have been much bigger actually. If I assume that it is not moving, system doesn't move, for example, in that case, quite obviously, this 5 into G will become tension. Had there been no movement, if there's no movement, in that case, thread tension must be equal to 5 into G, that is 50 Newton basically. In which case, if I notice the downward force that this body experiences because of gravity, assuming there's no friction actually, in that case, the backward force is going to be 8 into sine 30 degree, 8 mg sine 30 actually, so it becomes 4 into G, which is 40 Newton. So in this case, the downward force will be 40 Newton. Say the thread tension is 50 Newton, assuming there is no motion. Fine. So right now there's a difference of force 50 Newton this way and 40 Newton this way. If there was no motion, then the friction should provide the residual of the force. But the maximum friction we end up getting. Okay, fine. The maximum friction then can be only mu into the normal reaction. The normal reaction in this case, the maximum friction if I see, that is mu times the normal reaction, which is going to be 0.01 into 8 into G into cos 30 degree. 8G into cos 30 degree is what I have. But that makes it in this case 0.01 into 8 into 10 into root 3 by 2 Newton. That gives us roughly how much? 4 into 0.4 into root 3.
So 0.693.
How much?
0.693.
Okay, approximately 0.69 Newton, roughly. In this case, it is not enough to provide the required difference in the force by difference in the force of 10 Newton. This friction at worst possible scenario can provide only 0.69 Newton, not even 1 Newton by the way, which implies this block will have to go that way because the rightward force is upward force is more, and therefore the block will accelerate that way over there. Okay, but once we know that this is going to accelerate, now it becomes a simple matter of writing the equations. So the acceleration is a downwards, in which case for this block I end up getting the equation 5g, the gravitation, minus thread tension. This time it is no longer 5g by the way, okay, because there's no equilibrium. So now the thread tension is gravity pulling it down, 5 into g. The thread tension pulls it up. In this case the tension is this way, the friction is that way. mg is downwards, 8 into g, and there's normal reaction that way. That's what we have got so far. Yes, Atri, I was just saying that there, in this case, the block of 8 kg will have to slip up the incline because of the fact that the net force upwards, assuming equilibrium, is more than net force downwards, and so it's going to just go upwards over there. So I just do now the FBD, and we got out an equation over there. For the 5 kg block, we have got 5g pulling it down, thread tension pulling it up. So difference is 5g minus d, and this must be mass into acceleration, 5 into a. For this block, the tension is upwards, minus. You see that 8g has a component down incline, which is 8g sine 30 degrees. So I get 8 into g into sine 30 degree. And because there is sliding friction present, the friction force also acts backwards, which is mu into n, which is nothing but F max because sliding takes place over there. So I get minus mu into n. N is nothing but 8g cos 30 degrees. These are the net.
Sir, I got and solved these, and I got the acceleration as 0.7159 approximately.
Yes, sir. So for me also, it's coming the same. The equation is this only, but and the answer, acceleration is coming as 0.7 something.
Maybe I have made a mistake then. Let me see. Okay, let me see. Hold a moment. This
Sir,
must
because sir, from here we can directly write that.
actually, yes, I made a mistake. I actually wrote, I don't know what here is.
Sir, that's also coming for me.
Yeah, I actually wrote down 4A actually. It will be 8A actually. I wrote down 4A in fact.
Okay.
There, yes, I made a mistake actually. This was, I wrote down this one. It should have been 8A. In my copy, I wrote down as 4 actually. That was the trouble. So divide by 9 instead of 13 in fact. So yes, you are right. I'm wrong in that case. It will be 8. Fine.
Did
Okay.
you do with 9.8 G? 9.8?
G.
Did you? Yes, sir.
No, I took as 10. But what I did was, I actually keep, because what I was doing I mean rough. So I had already made this sine 30 degree, 8 sine 30 as 4. This one I also wrote down 4 over there because sine cos 30 will be root 3 by 2. So I wrote down this one for as 4 as well. It should have been 8.
Oh,
Okay, that is what a mistake. I started divided with 9 instead of 13 actually. Okay, just take a snapshot by and send it. That was my mistake then. I made a mistake in this case. That is a trouble when I do it very fast, or chance of mistake become too much. Anybody's taken a snapshot?
Yes, sir.
Fine.
yes, sir.
Okay. So these are 2 questions we have. So the answer is 0.7 something, but okay, that is okay. I made a mistake then. In this case, therefore, we can just add 1 and 2. Take the tension, cancels out. I get 5G. You already know that 8G sine 50 is nothing but 4 into G. And that becomes mu is 0.01 into 4 root 3G. We just did the calculations over there. This must be 13. This was a mistake. I divided by 9 actually. So it turns out to be You can do the calculations. 5 minus 4 is 1. And so it turned out to be 5 minus 4.69 approximately. 0.69 was there or 0.69? We calculated just a moment earlier.
693.
0.693.
Yes, sir.
0.9.
Oh, that is after putting the gravity, isn't it? That is after putting the G value. If I don't put G, it will be 0.069 actually. That was only obtained after placing the value of G as 10. Okay. In this case, I'm just taking it separate. G is now over there. So it will be 1 decimal more. Yes, Rishabh. I mean, I actually assumed that because I didn't know which direction of friction going to act. So I have to figure that out. That is why I first assume what happened if there is no friction. So then I find the direction of motion. And once I switch on the friction, the direction of friction, once I switch on the friction, it will not reverse the motion. It cannot retard it. So the direction remains the original, whatever you have obtained actually.
Assume that it moves. If it comes negative, it will be in the opposite direction.
No, that will not work, by the way, because if we assume it comes negative, the friction also switches. So you have to change. You have to actually, if it's coming negative, you can get the correct answer by switching two things, by replacing mu with minus mu as well. Okay, it will not be a simple matter to simply change the sign, because if the direction of acceleration was downward, for example, in that case, the friction would have acted upwards, isn't it? So whatever answer we get, upon simply putting a minus sign, it will not work. We have to then put a minus sign in the place of mu as well, to make it minus mu as well. Anyway, so how much is now I'm going to get? I think 0.7 something would have been the correct answer.
0.716.
Okay, 0.716. Maybe round up to 0.72. Yes. So, no, it is 0.69 something, by the way. Again, made mistake or what?
No, sir, it's
No, sir, it is coming.
716.
Sir, sir, I also did the same, but it is coming, sir. 5 minus 4.069, it will be 0.937. And, and,
0.9
and if
is 0.931.
One.
It's 0.931.
0.937, it is coming.
And I'm
Sir,
just
how?
doing a calculator.
Sir,
By the way.
4.0693.
Oh, take it, just wait. I'll just do the entire calculation once. It is 4 into root 3 into G into 0.01. Yeah, same as 0.1. So I get 0.693 actually. Okay, that's fine. Add to this 440 rather, plus 40. This must subtract from 50 and divide by 13. The turn 0.716. Okay, fine. Take it as 7.72. That will be better actually. 0.72 meter per second square root half. That's actually okay. Okay, that's fine. Okay, next. In case, by the way, in this case, can you tell me last sum? Ishant, last sum implies? Which one? Oh, now, yes, now. Yeah, it will last sum now actually. Let us see. Actually, what I was asking is, in this case, what might be the possible range of the other block which will not allow this? Fine, I'll ask that later on. Just now, write down, take up another question. We have in this case a block in which another block is placed. Threads are massless and frictionless. and this is being pulled with a force F, which is 80 Newton. This is say 10 kg. This is 15 kg. In this case, there is no friction, smooth surface. This one, there will be friction of 0.6, mu is 0.6. Okay. In this case, first of all, you will have to draw the FBD of all the objects. That you can do, and just tell me later on by the way. We don't have much time. So the question over here is to calculate the acceleration of this wedge, the block, the bigger block. If the system starts at rest, what will be the acceleration of this 15 kg block? That is what I want. Copy the sum and determine what is the acceleration of this 15 kg block. Assume that the pulleys are massless and frictionless. The thread is also massless and cannot stretch. And in effect, you can think that the pulleys are part of the block itself. Okay. The frictions, in any case, by they simply transmit the force to the block, the bigger one. The lower surface is frictionless, but the surface, the upper surface, over when a smaller block is placed, that has some friction, and the coefficient is 0.6. Four. No, that's not correct. But 1.333333 meter per second square. What is the question? The question is to determine the acceleration of the block, this 15 kg block. This is the one we have to figure out. Shubham, 3.2 meter per second square. How to get that? Abhijit, 4 by 3. Ishant, what is 4? Are you talking about 4 meter per second square? Riktam, 6 meter per second square is not okay. 4 meter per second square is not correct. 4 by 3 meter per second square is not correct. The correct answer is 3.2 meter per second square. Yeah. Shubham, how do you get that? Can you explain? By checking the acceleration of bodies together. Okay. So in effect, in this case, friction was enough to provide the required acceleration. Yes, fine. The maximum friction in this case is turning out to be mu into n. That makes it 0.6 into 160 Newton itself as a maximum friction. You see, in such cases, at least 2.4. No. Ishan, the answer is 3.2 meter per second square. The answer is 3.2 meter per second square. See, the idea is that in this case, I mean, because there's no friction at the lowermost surface, so even if it's a very small force applied, at least this entire thing is going to slip. That much is quite sure actually. But do not know whether there is going to be slipping over here or not. Okay, that I'm not sure about. So I can't just take F as mu into N. In fact, the usual way that we approach such problems where we do not know actually whether they're slipping or no is to first assume that they do not slip. The idea is to first think of what will happen if there's no slipping. If there's no slipping, they will just move together, isn't it? If it happens, for example, there's no slipping present in this case between the two bodies, if there's no slipping happening, or if there's no relative motion, if there's no relative motion, in that case, they will just move together by a single body, and therefore the acceleration will be, the common acceleration turn out to be F by the total mass, which is 25 kg. That makes it 80 by 25 kg meter per second square. That is when they do not move. So just 16 by 5. This is the common acceleration had the slipping not been there. Okay. Now the point is whether or not this particular acceleration will be supplied by all the forces acting on the blocks. In this case, if I look at the forces acting on this 15 kg block, by the FBD of 15 kg block, what will be that? FBD of 15 kg block. What we find is we have the force of gravity pulling it down. Then you have a contact force over there, the normal reaction pushing it up. Let's call it as N1. This force acts on this 15 kg. This force also acts on the same direction, same block. Then you have F pulling it down, F pulling it down. Then we have F pulling it this way, so we're pulling it that way. And then we have from this contact a normal reaction force pushing it down, and there's a friction acting in the forward direction actually. For this one, in this case, at the contact between, okay, at the contact between these two, actually the friction will act on the lower block in the forward direction. In fact, on the upward block in the backward direction, because what will happen is there's no friction. What will happen is, say there's no, say had there been no friction, then what will happen in this case? You might find that if there's no friction, the net force on this block is simply cancelling out. So it will stay over there, but this will go this way. Had there been no force, you can see that so far if there's no friction, F cancels out. So there's no horizontal force acting on a 15 kg block. And so what will happen is that will stay over there, but this block will go this way. So with respect to this block moves this way. So it will exert a friction on this block in the backward direction. And therefore the smaller block will act on this 15 kg block, a friction in the forward direction. And that is why on the lower block, the friction is also acting in the forward direction. In this direction, we have friction. So in effect, what I noticed is that looking at all the forces, if I look at all the forces, I find that the horizontal forces on the bigger block, there's only one surviving, which is nothing but F, this F, the friction. So we should have therefore that friction must be equal to then 15 kg into the acceleration, which gives us 15 into 16 by 5, that gives us 48 Newton. So if I assume that these two blocks move together, okay, if the two blocks move together, I'm getting that the friction at this contact which is required is only 48 Newton. But what about the maximum friction, by the way? At this contact, the maximum friction, if I calculate the maximum friction, that is nothing but mu into N. N is simply for this block, mg is pulling it down, and the normal reaction pushes it up. This is thread tension, that's the backward friction. So for this case, the maximum friction is nothing but mu times N, and that turns out to be nothing but 0.6 multiplied by 10 into 10 and that gives us in this case 60 Newton actually. So maximum friction turns out to be 60 Newton. Why?
Sir,
Yes.
So this can be also done by another way. First, this Fs max is 60 Newton, and the acceleration of the whole system is 3.2 meters per second square. So
That is only
therefore,
assuming, that is only assuming if they move together. Okay.
yes, sir. But if we means if we calculate the force which is acting on the 10 kg block, then it is
Yeah.
coming to be 10 into 3.2, that is 32 Newton, and
But
so which is less than.
that is already by assuming that there is no relative motion. That's what I've done essentially. If you calculate the force, then 10 into 3.2 is the net force, that is 32 Newton. So what you're saying is that the tension 80 Newton is the forward force, and then we have 60 Newton. What the friction? 80 is the
Uh,
forward force. So
no, sir.
friction must be
The Newton
48
is the
Newton.
maximum force which is provided by provided by the friction, and 32 Newton is the force which is acting currently on that 10 kg block when the force is 80 Newton.
Yeah.
Because the acceleration of the whole system is 3.2, and the mass of the 10 kg block and the mass of the small block is 10
Is
kg.
the resultant of the tension and the friction. Tension is 80 Newton minus the friction, that is 32 Newton. So
Yes, sir.
T is 80 minus F is 32, so F becomes 48.
Oh, okay, sir.
So I did that by looking at this one, so that I have to just consider only one force. Can do it anyway, by the way. But the point is
Okay,
that we
sir.
get 48 Newton, which is less than the maximum friction. Maximum friction 60 Newton, and we are getting the required friction to be only 48 Newton, which is enough, and that implies that they will move together. Had it happened, for example, that the applied force is large enough, say for example we apply 120 Newton, for example. If I apply the force to be 120 Newton, in this case, if I apply 120 Newton, for example, this is a bit confusing. Okay, we shall. It's too late, by the way. Next time we should discuss again over there. Fine. Let it. Write down the solution. Just check it whether you're getting or no. The main idea is to just assume to start. We first start by assuming that the okay, 3 was outside. Interesting. I was saying that first of all, we start by assuming that there is no friction, there is no slipping rather. We shall start by assuming there is no slipping. So when there is no slipping, they will move together as a single object. Then find the common acceleration and try to see whether the force of friction is enough to provide that. If it is enough to provide that required force, it will be doing that. But if it's not enough, in that case, there will be slipping. For example, if the force is 120 Newton, I do the same way. I get 120 by 25. But this time, if I calculate the force on this 15 kg block, I'm going to end up getting 15 multiplied by 120 by 5. Sorry, what I've done. 120 by 25 actually. 120 by 25. If I was saying that if this force is 120 Newton, in that case I would have got the acceleration as 120 by 25. So that the friction would have turned out to be 5, 3, 15, 5, so I get 24 into
So 180.
what?
180.
How much?
180.
180. No. 72 Newton is what I get. You see, if I take this 120 Newton over there, then this becomes 120 by 25. 120 by 25 becomes how much? We get 525 and 24 by 5, isn't it? This will become then 15 24 by 5. What am I doing by the way? 525, 5 2 10, 5 4 20. So I'm going to get 15 multiplied by 24 by 5, that makes it 72 Newton. Okay, but then the maximum is 60 Newton. So in this case, it cannot provide the required for acceleration, and so there will be slipping actually. So had this 120 Newton, then there will be relative motion between them. But once there is relative motion, I already know the friction value. It is going to be 60 Newton. There is a maximum it can act. So I know now that, okay, for this block, we have 120 Newton acting forward, 60 Newton backwards, net force 60 Newton forward direction. So the acceleration of this one becomes 6 meters per second square. But this will be different because for this case, the only force acting is the friction, because net force is just under friction actually. So in this case, we get friction in the forward direction, which implies 16 Newton divided by 15 becomes 4 meter per second. So that is then the acceleration of the lower block, if the force is 120 Newton actually. So main idea whenever we have this, I will just take up some more question next time, by the way. This is a bit complicated, I know that. The main idea is to start by assuming there is no relative motion and check whether the friction is less than maximum friction or no. Okay.
So, sir, so will we try this one using 120 Newton or 80 Newton? This question?
Oh, originally the question for 80 Newton, isn't it?
So we will take 80 Newton.
Yeah, that's all.
Okay, sir.
Okay, as a homework, what you could do is you can determine what might be the maximum value of F for which the two blocks move together. Okay, as a homework, you just take up the question where F is now no longer 80. Just figure out what is the maximum value of this F for which the two will move together actually. That will be your homework. Okay. I shall take up some more question of friction next time like these, because there's always some problem with this. So we shall take up some more questions. Meanwhile, for today it will be all. You can just leave, have your dinner.
100 Newton.
Okay, fine. If you take GS 10, then it's 100 Newton. That's fine. So homework is done then. There's nothing homework. I just send some more question later on. Yes, Priyanjana is correct. 100 Newton is the required answer. For 100 Newton, they will just move together till 100 Newton rather. Once after the force is more than 100 Newton, they will be slipping present. That is why for 120 Newton, we were getting some slipping over there. Okay.
100 Newton is coming.
Yes, that's fine. 100 Newton is going to be the required answer. This is 10 G. Anyway. So we finished today. Next time, take up some more questions. I shall possibly send you some more questions meanwhile, so that you might attempt them before the next class. And that will be all. You can just go have a dinner. Good night. Okay.
Thank you, sir.
Okay. Bye.